Okay, so first of all, I'd like to thank to the organizer and the program team of ICTS for having such a nice conference in this difficult situation. When I was told that the meeting in May was canceled, I was really disappointed, but now I'm happy that I can give talks in this situation. So I have 3 slots of my talks, and I'd like to give zero mean curvature surfaces in Euclidean and Lorentz-Minkowski 3 space. So the main topic of this meeting is zero mean curvature surface in Lorentzian space. But this topic is highly related to minimal surface theory in Euclidean space. So in this talk today, I'd like to give a brief review, quick review for minimal surface theory in Euclidean space. But you know, of course, there are a bunch of important results for minimal surface theory. So the topic I give today is only a part of theory, which will be related to my second talk and third talk. Okay, let's start. So I mainly consider surface in R3, but for a moment, we start from hypersurface in Rn+1. Okay, and local stuff, I will say. Let U be a compact set in Rn and local coordinate here. And let F be immersion from U into Rn+1. And G is an induced metric on U by F. And the volume of F is defined by this way, where dV is the volume element of F. Okay, and then C infinity map capital F from I times U, where I is a short interval, into Rn+1 with the following 3 conditions is called the smooth variation with fixed boundary of F. Well, we just simply say variation of F. Condition 1 is F sub t is equal to capital Ft. This is a map from U into Rn+1. This is immersion for any t. And F sub 0 is Fu, if it coincides with original F. And F sub t, U, is equal to original F where if U is in the boundary of U. Okay, so boundary unchanged, and F sub 0 is just the original surface, hypersurface. So in this case, we say capital F is called variation of F with fixed boundary. And let F be an immersion and big F variation of F, and nu t, the unit normal vector field on U along F sub t, and H sub t, the mean curvature of F sub t, and dVt is the volume element of F sub t. Then we have the first derivative of volume of F sub t equals to this. Okay, this is not easy, but just calculation. And when t equal to 0, we have the first variation formula for the volume of F. So that is this formula. Okay. So where nu is just nu sub 0, and h is just h sub 0, and dv is just dv sub 0. And from this variation formula, we have, so the first derivative of volume is equal to 0 for any variation of F, if and only if H is identically 0. Okay, so from this to this, if H is identically 0, then first variation formula immediately follows to this condition. But the converse is also true. So we have this. theorem. Okay, so, and now we know that F minimizes the volume for given fixed boundary if and only if this inequality holds for any variation of F. And then this holds, the first derivative of volume F sub t is there for any variation of F. Okay. And the previous theorem said this is equivalent to this H is identically 0. So the volume minimizing hypersurface satisfies H equal to 0. So how about the converse? So to think about this, under the assumption, I mean, H equal to 0, then compute the second derivative of volume Ft. Okay. And then after the long computation, we have this second derivative of volume F is equal to this. Okay. So then we set beta as a normal part of this vector. Then we have this equation H, the derivative of Ht equal to the Laplacian of beta and beta times A, where A is the second fundamental form of F, and this is Laplacian with respect to G, the first fundamental form. Okay. So therefore, we have the second variation formula for the volume of F. So using this fact, we have the second variation formula. The second variation is is written this way or equivalently this way, where this nabla G is the gradient with respect to G. Okay. So if beta is identically 0, then this is always 0. And this is called the trivial variation. And we think about the stability. First, we define the stability. Suppose that the first variation of F vanishes for any variation. That means H is identically 0. Then F is stable if the second variation of F is positive for any non-trivial variation. Okay. So we have this proposition. Let F be an immersion such that H is identically 0, and nu the unit normal vector field on U along F. And if nu U is contained a hemi-hypersphere, then F is stable. So one of results from the second variation formula, we have this proposition. And to prove this, the key equation is this identity. So I don't give proof of this proposition here, but this is a well-known result. And corollary, as a corollary, we have this graph hypersurface is always stable. And in fact, this is volume minimizing. This is a well-known result also. So this is one of result from the first, second variation formula. And I'd like to show the stability of the catenoid. Can you see the video? Now yes. We have, okay, thank you. This thin catenoid here. Maybe this is hard to see, but there's a soft film between two wire circles. And
we can see it. We can see it clearly.
Thank you.
Yeah.
Thank you. Now stable catenoid becomes unstable. Then catenoid collapse and separates to the two planes. So here, this is the stable catenoid. In this case, it looks like almost cylinder. So the image of Gauss map is like equator. And here, then the image becomes a thin strip, right, in S2.
Right.
Then if we change the surface this way, then the image of into normal getting bigger and bigger. And then some part, the surface becomes unstable, then collapse into two planes. And one can compute where is the critical value for the catenoid to be unstable by using second variation formula. Okay. And okay, there's one thing I think is interesting is when catenoid collapse to planes, then the tiny sphere appears in the middle of the surface. Can you see here, this surface?
Right. Yeah.
Yeah.
Tiny sphere. Yeah.
Tiny sphere, yes.
I saw, yeah.
Yeah. And I don't know why this happens, but somebody said this is always happened, and I don't know why. So if you know something about this, please let me know. Maybe physicists knows.
Yeah, they see it even in our soap film experiments in ICTS. They see it, yeah, and they have some explanation. Yeah, it's PD stuff. Okay. I don't know.
Yeah, thank you. Okay. So this is kind of a soap film experiment for stability of catenoid. Okay. Okay, let's go back to the talk. So, and by the first variation formula and second variation formula, this is that the surface with H vanishes, then have the properties that the surface is local area minimizing. So we say the surface with this condition is called minimal hypersurface. So okay, the catenoid, you have seen the catenoid before, and also we have helicoid. Okay. Oops. So helicoid, as a wire frame, we have one vertical segment and horizontal segment and spiral, then another horizontal segment. Then we have a helicoid as a soft film. And also circle, but wrapping twice. We have Mobius strip. Yes, this is a minimal surface. So non-orientable surface, mean curvature cannot be defined, but zero mean curvature can be defined. So this is such a surface, non-orientable minimal surface. And so we have many surfaces. And also I will notice that stable minimal surface and area minimizing surface. As we have seen, area minimizing surface is a stable minimal surface, but the converse is not always true. And let me show another soft film experiment. Okay, now we consider this wireframe. One of two circles are connecting a tiny neck. Okay, now film, you see that soft film, this horizontal plane and horizontal plane, and connecting this neck. Okay, so this is one of stable minimal surface. But then I will deform this surface. Can you see? Now this surface looks like part of catenoid. Okay, So first, the surface is like this: two horizontal plane connecting with tiny neck, tiny bridge. Then it changed to like part of catenoid. So with this frame, both are minimal surface with this boundary. So both are stable minimal surface. And one of them is area minimizing surface, and the other is not. And I don't know which is which. So, but both of them are stable minimal surface. Okay, so so area minimizing surface is always stable minimal surface, but the converse is not true. Okay. Okay, now we go to graph hypersurface. Let U be a domain in Rn with this coordinate, and let phi be a function on U. And then the mean curvature of the graph hypersurface phi satisfies this equation. This nabla and dive is usual gradient and divergence. And so this equation, this PD is called the minimal hypersurface equation. And when n equal 2, we set x, y equal to u1, u2, then the above equation is equivalent to this equation, this PD. This is first derived by Lagrange. And this equation is called the minimal surface equation. Okay. And I'd like to introduce the Bernstein problem. Now, this is classical, but interesting. The theorem by Bernstein is that the graph minimal surface defined on the entire R2 must be a plane. So the function phi defined on the entire R2 and satisfying minimal surface equation must be a linear function. So so generalized version of this theorem is called the Bernstein problem. So if it's a graph minimal hypersurface defined on the entire Rn, a hyperplane, this is a Bernstein problem. And this problem is formatively solved by Bernstein for n equals 2, and n equals 3 case solved in 1961, and n equals 4 case formatively solved by Almgren in 1966, and Simons for n equals less than or equal to 7. But then the problem is negatively solved by Bombieri and so on when n is greater than or equal to 8. So something happened between n equals 7 and 8. Okay, so tomorrow I will give the theorem for maximal surface version of this theorem. So today I will just notice for minimal surface case. And so this is kind of famous, interesting theorem for minimal surface. Now I move to the I will show some examples of minimal surface. And now we assume that n equal to 2. I think the first non-trivial minimal surface was found by Euler, and he found the catenoid in 1744. And then Meunier proved that the helicoid is also a minimal surface. And in the 19th century, Scherk found some new examples. And before Weierstrass representation, we only have these equations, these minimal surfaces, complete minimal surfaces. And it is well known that minimal surface with constant Gaussian curvature must be a plane. And also, minimal surface of revolution must be a plane or a catenoid. Or Rule's minimal surface must be a plane or helicoid. Also, translation minimal surface must be a plane or a doubly periodic Scherk surface. So before finding the relation between minimal surface and complex analysis, it's very hard to find solution of minimal surface equation. So these surfaces, they can find the solution of the minimal surface equation by reducing the PD to ODE by using some assumption, the surface of revolution, or ruled surface, or translation surface, something like that. So without this assumption, it's hard to find new minimal surfaces. But then, before going to Weierstrass, so this is Scherk's doubly periodic minimal surface and Scherk's singly periodic minimal surface. Okay, so I go to Weierstrass representation. So this is a very strong tool for minimal surface theory and to construct new minimal surface. Okay, let F be an immersion from U into R3. And XY is called the as thermal coordinate if the lengths of F sub x and F sub y are always equal, and F sub x and F sub y are perpendicular. Okay, and then let nu, the unit normal vector field on U along F. Then by direct computation, we have F sub xx and F sub yy equal to 2 times h times u. So thus F is minimal surface if and only if each Fj is harmonic function. Okay. And this implies that there does not exist a compact minimal surface without boundary. So if there is a compact minimal surface without boundary, then maximum principle implies that these Fj are constant, and so F becomes a point. So there does not exist a compact minimal surface without boundary. And now we set z equal to x plus iy, and phi j equals to this. Then by this fact, we know that F is minimal if and only if each phi j is holomorphic one form. Okay. And then conformality condition implies this equation, and regularity of minimal surface, minimal surface immersion implies this inequality. And using this, we have F equals to 2 times real part of integral of phi 1, phi 2, phi 3. This integral means path integral from fixed point to variable. Okay, and we now assume that phi 3 is not identically 0. If phi 3 is identically 0, then this third component of the surface becomes constant, and the surface becomes a horizontal plane. So we assume phi 3 is not identically 0, and we set g this way and eta this way. Then g is meromorphic function on U, and eta is holomorphic one form on U. And using this g and eta, we have this expression. And this is a Weierstrass representation formula. Okay. And then the first fundamental form and the second fundamental form are given this way by using g and eta. Okay. And also, we set if nu be the unit normal vector field on U, and let sigma be the stereographic projection from the North Pole. Then we have G is the composition of this sigma and nu. So composition of unit normal and stereographic projection. So hence we call G the Gauss map of F. This meromorphic function we call Gauss map of F. So G has this geometric meaning. Okay, so we can construct minimal surface with just take one integration. But then here we take path integral. So there is a period problem. So I will explain this. Let M be a Riemann surface and G a meromorphic function on M, and eta a holomorphic one form on M, such that this gives a complete Riemannian metric of finite total curvature. If M is not simply connected, then this F might not be well defined. I mean, this F might be multi-valued on M. So we set this period of F to be this set. So for any one cycle, this integral. And if the period of F is just zero set, then F is well defined. I mean, F is single valued on M. So this is no problem. And if there exists a vector in R3 such that period of F is contained this one-dimensional lattice, then F is singly periodic. Sometimes we say just single periodic minimal surface as SPMS. And F is well defined. I mean, F is not single valued in R3, but F is single valued in this quotient space. Okay. And there is also a screw motion invariant single periodic surface, but in this talk I will omit this case. I just consider this single periodic minimal surface. And also, if there exists two linearly independent vectors v1 and v2, such that period of F is contained in this two-dimensional lattice, then F is doubly periodic. And F is not single valued in R3, but F is single valued in this quotient space. Also, if there exists three vectors, three linearly independent vectors, such that period F is contained in this three-dimensional lattice, then F is triply periodic. And F is not single valued in R3, but F is single valued in this quotient space, so in this three-dimensional torus. So this is a period problem. I will show examples of these minimal surfaces later. And also, the important property of minimal surface is symmetry. So to explain this, let F be a minimal surface and C a geodesic on M. And we set Q equal to eta dg. So this is called the Hopf differential of F. And this is a holomorphic 2 differential on M. And applying Schwarz reflection principle, we have the following proposition. So if the geodesic C satisfies this, I mean, so Q is 2 differentials. So if we put 2 vectors, then we got functions. So we put this velocity of C. Then if this is purely imaginary, then the composition of C and F is a straight line. So the image of the geodesic in R3 is a straight line. And moreover, Fm is symmetric with respect to this line. So this means we rotate the surface 180 degrees with respect to this straight line, then surface is unchanged. And also, if C satisfies here, in this case, the real Q of C prime is real, always real, then the image of Ci by F is contains some plane in R3. And moreover, Fm is symmetric with respect to this plane. I mean, so, so F has mirror symmetry. So these are very strong properties of minimal surface. So let me show the one of examples. Okay, this is famous Costa's minimal surface. And so this is 1/8 of Costa's surface. Okay. So this is the end of the surface. This is planar end. So this goes to infinity like a plane. And this is also an end. So this goes to infinity like a catenoid. So, but the other boundary, so you see this is a straight line. So the symmetry line, right? And also this curve is contained plane. Can you see this invisible plane, right? I hope you can see the plane here.
Right, yeah.
Okay.
Yeah.
And also, thank you. And also this curve, this boundary is contained the plane, right? So
yeah.
Okay, thank you.
Okay.
We'll make reflection. Okay, first, so the surface is symmetric. So now we first extend the surface with respect to this line, okay, by 180-degree rotation. So we have, okay, this surface. And then now the plane contains this boundary and this boundary coincide. So same plane, this boundary and this boundary are contained in the same plane. So we make reflection with this plane. Oops. Now we have this. And now these boundaries are contained the same plane, right? So now we make reflection oops. Okay, so then now we have entire surface with reflection. Okay. So drawing graphics, we can only write. We only have to draw the fundamental piece, and then repeating reflection, we get entire surface. Okay. So this is one of the important properties of minimal surface. And now I will exhibit many examples of minimal surface. Okay, first, in these pages, all of them are finite total curvature, so period problem is solved. So period set is just 0 set. Okay, so no periodic. For example, this is called the George Meeks minimal surface. Okay. So this is topologically sphere minus 7 points, 1, 2, 3, 4, 5, 6, 7. And this is minimal surface. And this surface, you see the self-intersection here, right? So the surface has self-intersection, but if we restrict one end, then one end looks like a half of a catenoid. So each end is embedded. So we can say this surface has a property that embedded end, but the surface is not embedded. Or okay. This surface is topologically genus 2 surface minus 4 points. So 4 points become ends of the surface, 2 catenoidal ends and 2 planar ends. Okay. So but these are so we add 4 points, then we get a compact surface of genus 2. I hope you can see how one can get the genus 2 surface. Okay. So these surfaces are period problem solved, completely solved. So now these are single periodic surface. You see the periodic direction here, right? Or this direction. So for example, Riemann's minimal surface. So this is single periodic surface. So this is one period, and this is one period. Okay, and this surface has a property that if we cut the surface by slice by horizontal plane, then the intersection is always circle. So really a circle, not ellipse, but circle. So okay, and also this is called the Karcher tower. So you see the surface. The surface. So one half of this is the fundamental piece of the surface. So we translate this part into here. So just translation. This part coincides this part smoothly, and we translate the surface into the top, and this part and this part coincide analytically, connect analytically. And in such a way, we have the single periodic surface. And this surface has 6 ends. One end here goes to infinity, one end here, one end here, one end is here, and here. So the fundamental piece of the surface is a sphere minus 6 point. But this is a single periodic example of linear surface. And tomorrow I will show the maximal version of this surface in Lorentzian space. Okay, and also here we also have doubly periodic minimal surface. For example, okay. So this is called Karcher mix Rosenberg. And this is topologically torus minus 4 points. So this is one end, and this one end. Okay. So since the surface is doubly periodic, this and this match analytically. So 2 ends go to top and 2 ends go to bottom. Okay. So this is doubly periodic minimal surface. Also, here are examples of triply periodic minimal surfaces. This is classically known Schwarz P surface. All of them are Schwarz surface. Maybe this is one of the easiest to understand. So this surface is triple periodic. Maybe you can see easily how one can get triple periodic. So this circle matches these circles, top and bottom, and front and rear and left and right matches identically, smoothly. Then we get genus 3, compact genus 3 minimal surface, right? In a quotient, 3-dimensional torus. So this is topologically a genus 3 Riemann surface. Okay. So, and also Schwarz made this surface by using the Schwarz reflection principle. And this is genus 3, classically known genus 3 triple periodic minimal surfaces. And then later, physicist Alan Shane constructed new triple periodic minimal surfaces. This is one of his examples. And this is a triple periodic minimal surface of genus 4. So this surface, okay. So top and bottom are circle as well, but there's no holes in front, rear, or right and left. But instead, there's a 4 like spout at the corners. So, but in this way, we also have a triple periodic minimal surface. So we want to, so I'd like to adding spout here or make handles here. So then superpositioning of two known examples, then we get these new minimal surfaces. So there is a way to construct this kind of new surface. So now we have holes, both holes and spouts. And this is genus 6, minimal surface of genus 6. Okay, so this is an example of minimal surface, triple periodic minimal surface. Okay, also, we will show the examples of Schwarz P and D. And in this case, the Riemann surface is defined by this hyperelliptic function. So this MA is genus 3 compact surface. Okay, and A is a parameter, this parameter. And the Weierstrass data is given this way and this way. So they are conjugate surface. And when A equals this value, this is almost 0.5152. Then we have symmetric Schwarz P surface. But then we change A, then we can deform the surface. But all of them are still triple periodic minimal surface embedded. So we have one parameter family of minimal surfaces here. So also Schwarz D case, we have one parameter family of surface. Okay, and we want to know the limit of the surface. So first we consider the case A equal to 0. So when now this is the surface with A equal 0.1. And then since this surface is triple periodic, we cut the surface and translate the surface. Then we first cut the top half, go to the under of bottom half, and then we move this part to here and this part to here and so on. Then we have this surface. So this and this are the same surface, just different cutting of the surface. So then you see this surface looks like two catenoids connecting this line. So when A goes to 0, then the distance of this catenoid getting far away. And finally, we get two catenoids, two separate catenoids as a limit. Also, Schwarz D surface, this is equal to 0.1, and we again change, we cut this and move to here, or cut this, moved here, or something like that, then we get this surface. So these are the same surface, but different view. And you see, now the surface looks like a parking lot. So here, the surface looks like helicoid, and also this surface is also helicoid. So two helicoid connecting this geodesic. And when A goes to 0, we get helicoids as a limit. And also, we consider the other limit. That means A goes to 1. So this is Schwarz surface of A equals 0.9. And we cut this part and put here, and cut this part, put this here. Then we get this surface. And then as a limit, this part and this part separate, and we get this singly periodic Scherk surface. Also, Schwarz D case, we get this surface as A equal to 0.1, and as a limit. So this part and this part far away, and so these are becoming end of the surface, and we have Scherk's doubly periodic surface. So we have this kind of deformation of surface, minimal surfaces. And we will show the maximal surface version tomorrow or day after next week. Okay. So now I'd like to introduce some theorem for minimal surface of finite total curvature. Now in the following, let F be a complete minimal surface of finite total curvature. And there's a theorem by Huber and Osserman that F a complete minimal surface of finite total curvature, then there exists a compact Riemann surface of genus gamma, and finitely many points in this compact Riemann surface, such that M is biholomorphic to this surface, compact Riemann surface minus these points. And moreover, the Weierstrass theta, G and eta, which is defined on this M, but these are extend meromorphically on M bar. Okay? So without essential singularities. And these removed points are called end of the surface. So now we set M equals this M bar minus finite points. The gamma genus can be 0, 1, 2, but n must be a positive number. Then there's a important inequality called Osserman's inequality. It is complete minimal surface of finite total curvature satisfies this inequality. So this is a total curvature, and this is Euler characteristic. So this inequality holds. And also, moreover, equality holds if and only if each end is embedded. So embeddedness end I explained before. So this is proved by George Meeks in 1983. And we remarked that if M is a compact Riemannian manifold, just compact Riemannian manifold, no immersion, just compact Riemannian manifold, then this famous Gauss-Bonnet formula holds. And also, if M is non-compact, complete Riemannian manifold of finite total curvature, then we have this inequality, which is called Conforsen inequality. So this means for minimal surface satisfies a stronger version of Conforsen inequality. And equality condition is also given this way. Okay. And since the Gaussian curvature of a minimal surface is non-positive, the total absolute curvature tau of m is this, just minus kdA is total absolute curvature. And also, it is known that minus k times dA square gives the induced metric of the Rukmini study metric on the CP1. So this equation holds. So by using this formula and combine this and this, we have the total absolute curvature is 4 pi. 4 pi is the area of the sphere. 4 pi times degree of G. So degree is now defined because G can be extended meromorphically onto the compact surface. And so, and the Osserman inequality, this equality can be rewritten, this and this relation can be rewritten this way. So degree of G is greater than or equal to the genus and number of ends minus 1. So, and let me show examples which satisfy the equality. When n is greater than or equal to 3, there are many examples which satisfies the equality of Osserman inequality. So these are kind of examples. But if the case any 1 or 2, the situation changed. Or if n equal to 1, the surface, minimal surface satisfying Osserman inequality of Osserman inequality must be a plane. And n equal to 2 case, the surface must be catenoid. So this is proved by Richard Shen. So one cannot make a hole of catenoid. So there does not exist genus 1 catenoid. But it is interesting that if we change the end like this way, wavy end, wavy. So this is like a n-part type end. Then one can solve the period problem. So, so there is genus 1 surface with minus 2 points, but 2 ends are not catenoidal ends. And also, if we add 2 tiny catenoidal ends here and here, so then one can also solve the period problem. So this surface is genus 1, topologically genus 1 with 4 ends. So genus 1 catenoid doesn't exist, but we change the end, then period problem is solved. Or also we add tiny ends here, then period problem can be solved. Okay. And finally, I will introduce non-orientable minimal surfaces. So this is the final part of my talk, today's talk. Okay, let M prime a non-orientable surface. In this case, mean curvature is not defined, but we can take multivariate mean curvature. Then F prime is a non-orientable minimal surface if M prime, the mean curvature with respect to any unit normal vanishes identically. And let F prime be a complete non-orientable minimal surface of finite total curvature. Then we can take a double cover where M is an orientable surface. Then the composition of F prime and pi, we set this F is an orientable minimal surface. So one can apply the Weierstrass representation. So then we take the Weierstrass data of F and let I be anti-holomorphic degg transformation with respect to pi. Then we have this composition of F mod I equals to F. Okay. And this is equivalent to the Weierstrass data satisfies these properties. Okay. So let F prime be a complete non-orientable minimal surface of finite total curvature, and G the Gauss map of F. And let I be the anti-harmonic disk transformation with respect to pi. Then there exists a unique G hat, which is a map from M prime into a real projective space, real projective plane, such that the following diagram is commutative. I'm sorry, this G is small g. This should be small g, not capital. So in such a way, we can, where this P naught is a natural projection. Okay. And in this way, we can define the Gauss map of non-orientable minimal surface. And since both of pi and P naught degree equal to 2, then one can define the degree of this G hat as degree G hat is degree G. Right? So I'm sorry, this is G, small g. And for the degree of G hat, Meeks proved the following theorem. For complete minimal non-orientable minimal surface, and let G hat the Gauss map of F prime. Then the degree of G hat and the Euler characteristic of this non-orientable surface, compactification of this non-orientable surface is congruent mod 2. So as a corollary, a complete non-orientable minimal surface of finite total curvature, then the Gauss map, degree of Gauss map satisfies greater than or equal to 3. So if the degree is 1, then the surface must be catenoid, and so which is not non-orientable, or degree equal to 2, then the surface doesn't exist. So one can easily check. And Meeks constructed a Mobius strip. So this is a degree G is 3. And Meeks showed that this is the only non-orientable minimal surface with degree equal to 3. And so the previous Meeks theorem, in this topology, degree of Gauss map must be odd. And for any odd number, there's a Mobius strip with degree G is this odd number. So there exists a Mobius strip with degree G equal to 5, 7, 9, 11, and so on. Also, later, 1990s, Francisco Lopez constructed a Klein bot, minimal Klein bot. So this is topologically Klein bot minus 1 point. And this is this satisfies degree G hat equal to 4. So and later, Lopez showed that this is a unique non-orientable minimal surface with degree G hat equal to 4. So tomorrow I will explain the maximal surface version of this kind of Klein bottle. Okay, I stop here. Thank you very much.
Thank you very much for this nice and beautiful talk. If there are any questions, please raise your hand and I will call out your name. Please ask questions. So I have a simple question to begin with. Yes. So for minimal surfaces, I mean orientable minimal surfaces, you had for every genus and any number of punctures, you had a minimal surface of finite total curvature. Is that right?
Yes, yes, yes.
But for non-orientable, what is the story? Any genus can be realized, or?
Yes, if one can, for any topological type, one can construct.
One can construct yes, non-orientable.
Yes, okay. But we restrict degree of G hat, then sometimes non-existence theorem arises.
Yeah, right.
or embeddedness or something like that.
Okay, Epstam Taha has a question. Please ask.
So first, thank you. So in your presentation, you said something about non-orientable surface and the mean curvature cannot be defined. So I don't get why.
Okay. So mean curvature is defined by using unit normal, right?
Okay.
But non-orientable surface, unit normal is not well defined. So sometimes, okay, we want to take unit normal here, but go around, then sometimes change the orientation. So then if here mean curvature equals +1, then another way mean curvature is -1 or something like that. But the absolute value of mean curvature is defined for non-orientable surface. Mean curvature is just a trace of shape operator.
Yes. Okay.
Yeah.
Okay, and there is equivalent definition like in Riemannian geometry, like d by dt log sigma, and sigma is the volume form. Sorry, the volume density.
So you are talking about the orientation?
Yes.
Yeah, orientation. Yes, yes, yes.
Okay. Okay, thank you.
Okay.
Other questions? Please ask. Okay, so I would ask you all to go view the ICT lecture in ICTS talks when it's recorded and uploaded, and if you have questions later on, you can ask.
Okay.
Yeah. Okay. Thank you so much, Shoichi, for the wonderful talk.
Okay. Thank you very much.
And yeah, so see you tomorrow.
Tomorrow. Okay.
Yeah. Okay. Thank you.
Thank you very much.
Thank you so much. Okay.